Earth's magnetic field is really formed in the outer core, right? Now there are these currents that kind of look like spring-like swirls, and because Earth is rotating around its geographic pole, the molten material in the outer core is also rotating and causing really a dynamo, and we call it the geodynamo. And whenever you get currents moving, you develop either electrical fields or magnetic fields. And remember, you're always going to have a magnetic field when you have an electrical field. And so we're going to develop this very pretty pervasive magnetic field that surrounds the planet. And we already talked a little bit about this, right? So Earth's magnetic field is due to flow of material in the liquid outer core. The magnetic poles are not parallel with the rotational axis, right? So remember, this angle here is the angle of declination, and the angle that the lines of force make with our surface is the inclination, right? The inclination. So let's keep going here. So one thing that your book points out are these polar wander studies, and the magnetic pole does fluctuate, never more than about 1,500 kilometers from the geographic pole. So as we go along here, we'll see that there are maps, right, that showing what the magnetic declination is in your part of the country. For example, here in California, we're at about 12 degrees, 13 degrees to the west of true north, right? So if you had a compass, you'd have to correct your orientations for that. Yeah, so hence a compass does not point to true north, but rather to magnetic north, and the difference is the declination, and so you would have to take that declination into account to figure out where true north is. Now, remember, the curving lines are due to the field, right? And that's going to be our inclination, right? So we talked about the inclination. Again, if the rocks are forming near the equator, they're going to have basically an inclination angle of 0. But the higher you go in terms of latitude, the steeper the angle will be, right? The steeper the angle will be. And also kind of coming back to here's that dipole, right? So this would be the positive and negative end. But remember, for Earth it's a little bit different. This is magnetic north up here, and magnetic south would be down at the bottom here. Now, this is your books. I drew a little cartoon of this showing how when lava erupts, the magnetic minerals, the magnetite, are really randomly oriented, right? But then here's Earth's magnetic dipole, the Earth's field. The magnetic minerals start to align themselves. Again, they're acting as tiny compass needles, and they point in that same direction as Earth's dipole, or Earth's magnetic field. As the magma cools, remember, it's going to cool below that Curie point of 580 degrees centigrade. We're going to make a permanent record, right? The magnetic signature is then frozen in the rock, right? And so now we know we can go back and look at rocks that are millions of years old and figure out what Earth's magnetic field was at that time. Now, here's the example. Here's a rock, and the way we sample the rock, we take these cores of it, and we take a core of the sample, and then we measure the orientation of the magnetic minerals in that core. And in this case, you can see that they have an inclination. They're not horizontal, so the inclination is the angle from the horizon, right? And note that it's going to have a declination here, which is different than magnetic north is today. So obviously this is rotated some distance, right? So by doing that, by determining the paleomagnetic dipole of the rock, we can chart where these rocks have been in the past, right? So again, this emphasizes that rocks with really steep inclination are forming close to the poles. Rocks with shallow inclination are going to be near the equator, right? Near the equator down here. I'm trying to get this one in here. All right, so we'll review this. I have a worksheet we'll do on this later on. And then this is showing a continent here, and it's showing that, and these represent lava flows, right? They represent lava flows. You can see that 600 million years ago, the inclination is nearly horizontal, so it must be somewhere far to the south, right here, near the equator. Here's the equator. Then over time, we see that the inclination becomes steeper, for this continent, which means it must be moving to a higher latitude, right? Because that's where you see the steeper inclinations, right? So it's showing the path to higher latitudes, but then it seems to flatten out a little bit, which means we're going back to maybe a more equatorial latitude or closer to the equator. But then we see it get steep again, which means it's moving back to a higher latitude. So this is showing this continent is moving, right? So changes in inclination and declination in layered succession of lavas can predict the history of plate motion within a continent. So this records the plate motion for one continent, how it's moved. It was closer to the equator, then it went to mid-latitudes and kind of fluctuated, and then it changed over time there, right? Here, when we look at two separate continents, in this case, well, in fact, we're looking at three. We're looking at Europe, Africa, and North America. We see that each continent has its own independent polar wander path, right? So this is called the polar wander path. And we know there's only one magnetic north, right? So the only way to explain that these three independent polar wander paths is that these continents must have been together at some point in some supercontinent, right? So what does it say here? The apparent polar wander path of Europe differs from North America, proving that the continents and not the poles have wandered through time. So, but the key thing is if we reassemble these continents, so we'll look at them here, right? So here are the independent polar wander paths, but we reassemble them, then the two paths coincide, right? So it's really that the continents move and not the poles. So remember, this data came after Wegener proposed all his hypotheses and his criteria, but remember, he used paleoclimate zones. But by using the paleoclimate or paleomagnetic data, we can corroborate his findings in terms of paleoclimate zones. Again, the continents are moving, plate tectonics. Finally, let's end this with ultimately Alfred Wegener's continental drift hypothesis was rejected in the 1920s, and it was rejected because Wegener could not explain how, what mechanism, what was a mechanical system to cause these continents to move. Because one of the things the geologists already knew based on looking at seismic waves and earthquake waves is that the ocean crust has a thickness, right? And so how can you have a continent plow through a rock that's already there, right? So they were really confused, as it's like trying to walk through a wall. You just can't do it. So the ultimate rejection was really due that Wegener could not explain how continental drift worked. No mechanism. The other thing is, your book mentions that Wegener envisioned Pangaea to break up toward the end of the Mesozoic, around 65 million years ago. But paleontologists and biologists already knew that fossils differed pretty diversely by the middle of the Mesozoic and really the early parts of the Mesozoic, a time called the Triassic. And so we find, and also now with paleomagnetism, we find that Pangaea really started to break up about 180 million years ago, and that's during the Triassic, right? So his timing was off as well. But really, the main rejection was this no mechanism. Okay, well, we'll stop here for now.